Everybody, Mr. Smith here, and we're shooting our third lesson in our first unit on polynomial functions. And in this lesson, we're looking at connections between the finite differences of a polynomial function and properties between of the graph of that function, perhaps. So let's just get started. You guys are going to do an investigation where we look at some, fairly basic polynomials and look at their finite differences and just see if we can actually start making some connections, some theories that we can use later that might be useful to us. So you guys are doing 5, and I chose some polynomial functions that are fairly easy to make a table of values for. So for example, for y equals x squared, I expect most of you guys can just get these filled in with mental math. But 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Now, what we mean by finite differences, you guys have been doing these since your grade 9 math course, is the finite differences refer to like the first differences, second differences, third differences, and so on and so forth. So let's calculate the first differences together maybe for y equals x squared. And the first differences are simply, what are we increasing or decreasing by as we go from y value to y value. Fairly easy to do that with mental math for this one. We go up 1, then we're going up 3 from 4 to 9. That's an increase of 5, increase of 7, and then an increase of 9. As a general rule, to get any differences, you just subtract the lower value minus the higher value. It's just finding a difference. Those are the first differences. And we're going to keep going. Now we're going to find the second differences here. 3 minus 1 is 2. 5 minus 3 is 2. 5 minus 7 is 2. 9 minus 7 is 2. And wouldn't you know it, the second differences for this quadratic function are equal. That's something that you established in your grade 10 course, actually. Excuse me. What I'm having you guys do is look at the finite differences for some higher level polynomials, a couple cubic and a couple quartic. And so you might have to go to the third or fourth before you start to see a pattern. So if you'd like to, at this point, pause the video and try these on your own, and then just unpause when you're ready to take something up, you can. Or you can just follow along with me. Let's make the table for x cubed, 1, 8, 3 cubed, 27, 4 cubed, 64, 5 cubed, 125. First differences, 1, 7, 19. I'm using mental math here. I'm probably going to get myself into trouble. 37, and that looks like 61. Those are the first differences. Let's look at the second differences. 6, 12, 18, 24. Now this function is not quadratic, so we wouldn't expect to see the second differences being equal, but you might see a pattern right now. In fact, when you calculate the third differences for a degree 3 polynomial, like x cubed, we get 6, and they're all the same. Let's do another one with the cubic. So we're just to do minus 2x cubed to generate the table. We'll just take our values for x cubed and multiply them by negative 2. So 0, negative 2, negative 16, negative 54, negative 128, and negative 250. I know for sure I'm going to get myself into trouble with the mental math at some point, but not right now. Let's just keep going. All right. From 0 to negative 2, that's a drop of 2. So with all of our other examples so far, the first differences were positive because they were increasing. Here they're decreasing. From minus 2 to minus 16 is a drop of 14. You could also get that by doing negative 16, subtracting negative 2. Then we have minus 38, minus 74, and minus 122. If I've made a mistake and you're kind of screaming at your computer, don't worry. I'll catch it as we go along, but it should be okay. Now, minus 2 to minus 14, that's a drop of negative 12. Minus 14 to minus 38, it's a drop of negative 24. Drop of 36, and then a drop of 48. It looks like I did okay. If we now go to we've done the first differences, they were not equal. Of course, if they were, it'd be a linear function. Second differences were not equal. If they were, it'd be quadratic. We saw that the third differences were equal for y equals x cubed, and they're equal again for minus 2x cubed. It's just we get the third differences are minus 12. What I ideally would like you to be making connections with is, being able to predict, okay, here's this polynomial I have. What will I eventually know about the finite differences, and can I even predict what they are? Let's continue. So maybe you've had a chance to do these, maybe not. If you haven't, I would encourage you to pause the video, try these on your own, and unpause when you're ready to take it up. The quartic polynomial, the basic quartic. So 0, 1, 2 squared is 16. 2 to the power of 4 is 16. 3 to the power of 4 is 81. 4 to the power of 4 is, I believe, 256. And 5 to the power of 4, 625. Let's calculate the differences. First difference is 1, 15. I'm eventually going to have to whip out my calculator here. 65 is good. Okay, I'm going to tap out, and just so that I don't waste video shooting time, I'm going to suffer along with you guys and do some subtractions. I should be able to do this with mental math, but don't want to press my luck, And 369. Right, first difference is not equal. Of course they're not. It's not a linear function. Let's look at the second differences. 14, 50, 110, and then 194. The second differences are not equal because it's not quadratic. Let's continue. 36, 60, 84. The third differences are not equal, but that's okay because it's not cubic. If we go one more time and look at the fourth differences, 24 and 24. The fourth differences for a quartic polynomial are equal. And I think you probably see where this is going, but let's do one more. We're anticipating the fourth differences for this function to be equal. But one more thing we can maybe hopefully do is, we know for y equals x4, the fourth differences were going to be equal. But is there a rule we could use to actually predict the value of the fourth differences being 24? That's the kind of the one last thing to have you guys think about. But let's get this one done. So we're going to take all our values from before and multiply them by negative 2. So 0, negative 2, negative 32, negative 162, negative 512, and negative 1,250. Let's find the first differences. So negative 2, negative 30. I'm not going to be a hero with the mental math here. If I need to do it, I will on a calculator. Minus 350, and I think that's minus 738. Okay, I said I wasn't going to be a hero, and now I'm just being a hero. So let's just double check that. Plus 512. All right, perfect. So let's do the second differences. Again, we're anticipating the fourth differences being equal to see if this checks out. So from minus 2 to minus 30, minus 28, minus 100, minus 220. These aren't so bad so far. And that looks like minus 388. So that's the second differences. Let's continue with the third differences. This is a drop of 72. This is a drop of 120. And this is a drop of 168. That's the third differences. And look at this, guys. From minus 72 to minus 120, that's a drop of 48. And from minus 120 to minus 68, that's a drop of 48. The fourth differences are equal. Pretty cool. So let's consolidate here. And if you want to, if you've already had a look at these questions and thought about them and got something down, fantastic. If you haven't, I'd like you to maybe to think about what we just saw and see if you can answer these questions on your own. And you can just unpause when you're ready. But what's true about the finite differences, not a big deal there, for a quadratic function, a cubic function, and a quartic function? So for quadratic, I might just add in here, remember quadratic, degree 2. What's true? The second difference is equal. The second differences were equal. For a cubic, a degree 3 polynomial, the third differences were equal. For a quartic, degree 4, we saw the fourth differences were equal. And I think you guys see the pattern. If you had a degree 10 polynomial, not sure what the name of that one would be, but if you had a degree 10 polynomial, then what you would see if you did it that far is that the 10th differences would be equal. I don't know who would want to do that. Sounds like a lot of pain, but hopefully you get the idea there. That is a rule connecting the degree of the polynomial to the finite differences. For a degree n polynomial, the nth finite differences are going to be equal. Secondly, have a look, go back at R5 and look at the leading coefficient of the function and look at the finite differences. So let's go back to our first three. Positive leading coefficient, positive leading coefficient, negative leading coefficient, and look at the finite differences that were equal. Positive 2, positive 6, negative 12. It appears there's a connection there between the leading coefficient sign and the sign of the finite differences that are equal. Does that rule hold for the next two? It did. Positive leading coefficient, positive fourth differences were equal. Negative leading coefficient, the fourth differences here that were equal were also negative. So the sign of the leading coefficient. Now this isn't by any means proof, but hopefully you're convinced of this property after the investigation. The sign, of the leading coefficient is identical to the sign of the, I'll just say, equal finite differences. So suppose that might have been easier to type in and just have float in there afterwards. Now, those two connections you probably made, they weren't too overwhelmingly complicated. I imagine most of you guys kind of made those connections kind of right away. The next one's not so obvious, though. Can you spot a rule for determining the value of the finite differences given the degree of the polynomial? So given the degree n and the value of the leading coefficient a. Can you derive a formula? Can you see a formula given the degree n and the leading coefficient a that would give you the finite differences? So for example, for this first one, the degree is 2, the value of a is 1, and I'll just put the finite differences are 2. For the next one, n is equal to 3, a is equal to 1, and the finite differences are equal to 6. In our third one, n equals 3, third degree, a equals negative 2, and the finite differences were equal to negative 12. I won't do the last couple. This one, if you can't spot the rule, that's okay. It is actually a fairly tricky rule to spot. If you can, fantastic. If you can't figure it out, I'm going to give it to you basically right now anyway. But yeah, if you want to pause the video and just challenge yourself and see if you can figure that out, that'd be phenomenal. But here we go. Um, we're going to do a little summary. And in the summary, I will give you guys the rules. So let's kind of summarize what we spotted. For a polynomial function of degree n, where n is positive, the nth differences are equal. So degree 2, second differences are equal. Degree 3, third are equal. Degree 4, fourth are equal. Hopefully you guys are now convinced of that after our little investigation. You can do more functions if you want, more complicated ones, but this is always going to be true. So the nth differences are equal. The nth differences have the same sign as the leading coefficient. Hopefully you're now convinced of that. And a rule for determining the value of those differences is the following. The nth differences are equal to a, the leading coefficient, times n minus 1 times n minus 2, all the way down to 1, depending what the degree of n is. Now, those of you guys who have taken data management will likely know a more simple expression for this. Even if you haven't, maybe you already know. But if a nice way of writing n times n minus 1 all the way down to 1 is this. Instead of writing that big string of multiplications, you can just write that as n with an exclamation point, and this means n factorial. So for example, 5 factorial is equal to 5 times 4 times 3 times 2, all the way down to 1. And it's just a nice, concise way of writing that instead of actually writing out all the numbers. 7 factorial is just 7 times 6. You just tick it down by 1 every time. So yeah, that notation is just a bit handier. So if you were able to figure out that rule on yourself, good for you. Not really an obvious rule. That rule can be proven using calculus, but we aren't there yet. But now that we know the rule, we can apply it. Okay, so guys, that's the meat and potatoes of this lesson here. I actually considered lumping this lesson in with the previous one. I just found the last lesson was already kind of long enough. So let's just do a couple of examples with playing around with these new connections. So here I've given you guys a table of values. That's all I've given it, and it does represent a polynomial function. I'm not asking you guys to find out what that polynomial function is, but just from this table of values, we can determine the degree, the sign of leading coefficient, and the value of the leading coefficient. So let's dive in here. And the key to doing all that is finite differences. So we're going to calculate the differences until we get differences that are the same. So from minus 36 to minus 12, that's an increase of 24. Minus 12 to 2 is an increase of 10. Minus 2 to 0 is an increase of 2. And then 0 to 0, 0 to 4. Yeah, we're okay. 4 to 18, 14, and 18 to 48 is 30. Again, if you notice me make a mistake, at some point I'm gonna find it out because what I'm doing is not gonna work. But I think all that all looks good. 24 to 10 minus 14, and this is actually an interesting note. If you guys end up becoming math teachers, or really physics, chemistry, any kind of teacher teaching maths or sciences, it's definitely helpful to do problems ahead of time. Then you do not run into any embarrassing situations. 10 to 2 is down 8. 2 to 0 is down 2. 0 to 4 is up 4. 4 to 14 is up 10. 14 to 30 is up 16. Still not equal. Let's continue. Minus 14 to minus 8, that's an increase of 6. Minus 8 to 2, aha, increase of 6. Minus 2 to 4, up 6, up 6, up 6. What we have shown is that the third differences are equal, and the third differences are 6. We now know a lot about our polynomial function. So to answer part 1, the degree of our polynomial function is 3. It's cubic. How do we know that? is because the third differences are equal. Since the third differences are equal, all right, what do we know about the 2 and 3 could actually kind of be done the same at the same time, but what do we know about the sign of leading coefficient? It's positive. And this is because the third differences are positive. I'll just get that down. All right, now let's find out what the leading coefficient is in this case. So what we have here is we have the degree, n is equal to 3, and the finite differences that are equal to 6, and we don't know what a is. So we can set up our little rule that we developed. The finite differences are equal to the leading coefficient times n factorial. Let's plug in what we know. The finite differences were 6. We don't know the value of a, and n is 3. What is 3 factorial? It's 3 times 2 times 1. 3 times 2 times 1 is equal to 6, and that means that the leading coefficient in this case is 1. Now, there are methods for finding out what the actual function is. We're not really concerned with that right now. This is enough the connections we want to make today. Why don't you guys try part B? See if you can do it on your own. So pause if you want to pause the video and give it the old college try, and you can unpause when you're ready. Of course, then that would be preferable. Of course, you're always welcome just to follow along with me. So let's get going with the first differences. Here we go. Minus 54 to minus 8, that is an increase of, well, I got to be careful here. That's an increase of 46. Minus 8 to 0 is an increase of 8. 0 to 6 is an increase of 6. 6 to 22 is an increase of 16. 22 to 16 is an increase of, why can't I do that in my head? 14. 36 to 12, minus 24. And then 12 to minus 110, that looks like a drop of minus 122. So let's continue. Everything looks fine there. But yeah, as I said, if I've made a mistake, it's going to come out in the math. We're just not going to get finite differences that are equal. But that might be a fun exercise too, just kind of figure out where we went wrong. 46 down to 8 is a drop of 38. And then 8 to 6 is a drop of 2. 6 to 16 is an increase of 10. 16 to 14 is a drop of 2. 14 to minus 24 is a drop of 38. And negative 24 to negative 122, I believe, is a drop of 98. But I'm just going to double check that. Is a drop of 98. All right, let's keep going. See if we get one of these finite differences being equal. Let's go with third differences. So minus 38 to minus 2 is an increase of 36. Minus 2 to 10 is an increase of 12. 10 to minus 2 is a decrease of 12. Minus 2, decrease of 36, then decrease of 60. I'm seeing a pattern here. 36 to 12, drop of 24. 12 to minus 12, drop of 24. In fact, we have shown that the fourth differences are equal. So, which degree is this polynomial? It's degree 4. The fourth differences are equal. What's the sign of the leading coefficient? It's going to be negative. The value of a is going to be less than 0. And again, we know this because the fourth differences are negative as well. Now, let's find out the leading coefficient. So our finite differences are equal to negative 24. The degree is 4. And we're looking for what the leading coefficient is. So let's use our formula. The finite differences are equal to the leading coefficient times the value of n factorial. In this case, 4 times 3 times 2 times 1. 4 times 3 times 2 times 1. So negative 24 is equal to, that gives me 12. I guess I could just, actually that gives me 24. So I can just write 24 times a. And then, yeah, the value of a in this case is negative 1. The leading coefficient in this case, negative 1. All right. Pretty neat. Let's continue. I have one more example, and it's actually just more of what we've been doing, just a little tying in an application. So here we have an antibacterial spray tested on a bacteria culture. And this table represents over time the population of bacteria culture T minutes after it's sprayed. So as you guys can see, as the minutes increase, the amount of bacteria decreasing as well. And we're going to just proceed what we've been doing. We are going to use finite differences to see what the type of polynomial it is, right? So what is the degree of this polynomial, and find the value of the leading coefficient. Yeah, so give it a try, guys. And then in part B, we're going to use Desmos and a feature on Desmos to perform our regression. And we're going to determine an equation for the function that models this situation. Yeah, let's get going with part A. Actually, first of all, I would again remind you, I would encourage you actually to try the question first, and then pause and try the question, and then unpause when you're ready. But yeah, let's dive in here. Find the first differences. Down 1, down 17. Oh boy, these are big numbers. I can see myself getting into trouble. Down 45. Down 85. I'm going to check that one. 652 minus 737. Yeah, down 85. Down 137, it looks like. Down 201. I got to check these. 137 is good. 314 minus 515 is good. And 37 minus 314, negative 277. So it's not linear. Let's continue. Maybe it's quadratic. Negative 1 to negative 17 is a decrease of 16. And then we have a decrease of 28, a decrease of 40. I can see where this is going. We have a decrease of 52. This is a decrease of 64. And this is a decrease of 76. The second difference is not equal, but the third differences are going to be equal. Minus 16 to minus 28, that is a drop of 12. And then all the third differences are equal to 12. So we can solve part A. So for part A, what type of polynomial is it? It is cubic, degree 3. The reason why is because the third differences are equal. Since I'll just squeeze that in here. Differences are equal. All right. For number 2, the value of the leading coefficient. So the finite differences, I'll just write out my formula here. Finite differences, remember, are equal to a times n factorial. So here they are minus 12, the ones that are equal. We don't know a. And n factorial, n is equal to 3. So 3 times 2 times 1, that's 3 factorial. So minus 12 is equal to, that would be 6 times a. And so the value of a is equal to negative 2. All right. So I'm actually going to pause my screen recording and I'm going to get this data entered into Desmos so I can give you guys a little video tutorial on how to do that. And we'll actually find the equation of the cubic model that models this data. All right, guys, I've loaded up Desmos here, and I'm going to show you guys how to perform a regression. So we know that our equation is going to be cubic, and how do we determine? And we know the leading coefficient, but how do we determine the rest of the polynomial equation? So I'm going to add in a table here, and in this table, I'm going to enter my data. So our data went from 0 to 7, and I'll just pop in my y values, 799. I just have to flip back to my 799, 82, and 37. So 82, 737, 652, 515, 2, 515. It was 314. Yeah, 314 and 37. Now you can't see these points on our graph because the way my scale is, the scale is just doesn't show any of these points. That's okay. If you want to find an equation of a cubic polynomial that fits this graph, here's what we do. So to perform a regression, we want an equation like y equals, but I'm going to use y1 because I want to match it to my data table here. So y1, and then you use the tilde. It's usually shift and the number beside the 1. And a cubic polynomial has the cubic term, the quadratic term, the linear term, and the constant term. So 4 variables. I'm going to use A, B, C, and D for those coefficients. So we do A. So our equation looks like this. A, and instead of X, I'm going to use X1 to match my table there. And this is the cubic term. Plus B, X1, and that's the squared term. Plus C, X1, that's the linear term. Plus D is the constant term. And you guys can see that the program performs what we call a regression. It fits our data to a curve. And look, the function that fits our data points has a leading coefficient of -2, which we found out. The quadratic coefficient is -2. The linear coefficient is 3, and the initial value, the constant term, 800. So we can actually write out what this equation looks like. Let's head back to our note. And so the equation that models this linear function would be y equals, so -2 x cubed. Now we already knew that from our previous work with the differences, but the differences didn't tell us the other things. So -2 x squared plus 3x, I believe. Yep, plus 3x. And 800 we could have figured out because when t equals 0, the population was 800. So that's pretty cool. If you really wanted to, you could take, you know what? I really just should write that as p equals. I really should do that. Wouldn't feel right because it's p and t plus 800. So we'll just scratch this off here. If you wanted to convince yourself, take that polynomial function and plug in those values for t. It's going to match up perfectly. That regression tool can be very useful. We're going to pull it out at different times in the course. That's actually it for the lesson, guys. The big connections I wanted you guys to make summarized here. So if this made sense to you, fantastic. I think the first 2 of these points are pretty obvious and straightforward, but this formula for actually determining what the finite differences will be and using it to find the leading coefficient would be new to you guys. So what I have for you guys is a bit of practice from the McGraw-Hill-Ryerson text. In our next lesson, we're going to discuss what kinds of properties of a polynomial function we can get right from the equation so we can start doing some sketches. So specifically, we're going to be looking at a polynomial function, and we're going to be saying, okay, well, what is the end behavior? What are the zeros or the x-intercepts? And what is the y-intercept? And we're going to try to make some rough sketches of some pretty complex polynomials. It should be a lot of fun. There's no deliverable associated with this lesson, so no, I don't have a quiz or a assignment per se. But after our next lesson, lesson 4, I do plan on producing and posting a short assignment based on these two lessons, lesson 3 and 4. So stay tuned for that. But yeah, this practice here should reinforce what we just learned. And yeah, guys, hopefully you're enjoying the course. Hopefully you're having a good day as well. Stay safe. Have a good one. We'll see you soon.